Hi, welcome to a not very useful headline about floods. Recently, I saw a headline on AccuWeather.com. It read, "Dallas flooding is fifth 1-in-1,000-year flood event in the U.S. since late July." A link to the article is in the description below. Now, this headline implies a very unusual set of events has occurred. But just how unusual is it? Unfortunately, the answer is that we don't know, because we don't have enough information. So, instead of answering this question, here we're going to look at what questions we should ask to figure out how unusual this set of events is. I should say up front that I'm not claiming that the set of events described in the article isn't unusual. It might very well be. But this video is about additional information we would need in order to figure out how unusual this set of events is. There are a few videos on this channel that might be useful for understanding the content of this video. First, there are two videos on 100-year floods, called What's a 100-Year Flood? Parts 1 and 2. Second, the most important point of this video is about something called the look elsewhere effect, or the multiple comparisons problem. For more information on that, you can check out the video Why the Look Elsewhere Effect is Important. As 1,000-year floods are, in principle, described by the Poisson distribution, we will also be making mention of that. For more information, you can check out the Poisson Statistics playlist. And finally, you might also be interested in the video When We Think Events Are Independent and They're Not. Okay, first let's talk about two naive, and by naive I mean wrong, ways of looking at these events. Okay, so here's that headline again. Dallas flooding is fifth 1-in-1,000-year flood in the U.S. since late July. This headline is from late August 2022, so the time period involved is less than 5 weeks. The 5 floods in question occurred in Death Valley, California, Dallas, Texas, St. Louis, Missouri, Southeast Illinois, and Eastern Kentucky. Okay, so let's take a river. Occasionally, it floods. A 1-in-1,000-year flood, or more commonly a 1,000-year flood, is expected to occur, on average, once every 1,000 years. They are taken to have a constant probability of occurring per unit time, so they are described by the Poisson distribution. The probability of a 1,000-year flood to happen over the course of a given year is about 1 in 1,000. The probability of one 1,000-year flood happening in a given 5-week interval, which I'm just going to call a tenth of a year, is about 1/10 of that, or 1 in 10,000. Okay, let's take a look at what we'll call naive view 1, where here naive really means wrong. Here's how that goes. During this 5-week period, one of these 1,000-year floods occurred in each of these 5 locations. They should be roughly independent of each other, so the probabilities multiply. The probability of each flood individually to occur in the 5-week period was 1 in 10,000, so the joint probability was that to the 5th power, or 10 to the minus 20. This is a very tiny number. Okay, next let's look at naive view 2. Here we say the following. The occurrence of 1,000-year floods is described by the Poisson distribution. The expected number to occur in 1/10 of a year, which we will call lambda, is 1 in 10,000, or 10 to the minus 4. We want the probability to observe a number n of such floods, where here n is 5. So we use the Poisson distribution for lambda equals 10 to the minus 4 and n equals 5. We plug those two values into the formula for the Poisson distribution, and we get a probability of about 8 times 10 to the minus 23. This is even smaller than the previous estimate. In either of these calculations, we would conclude that the probability of observing these 5 floods in these locations during this 5-week period, under normal conditions, was ludicrously small. This would indicate to us that our previous evaluation of what we thought was a 1,000-year flood was flawed. In other words, a flood of a size that we thought would only come every 1,000 years actually happens much more often than that. Okay, now we're going to talk about why those results are both really, really wrong. Both of these results are wrong because they fail to take into account the look elsewhere effect. Okay, so we'd better briefly describe the look elsewhere effect, also known as the multiple comparisons problem. A seemingly extremely unlikely event may not be very unlikely if it has many chances to happen. To illustrate, let's take the example of a lottery. Imagine that in this lottery, a ticket has a 1 in 10,000 chance of winning. If you buy a ticket and win, that is a very unlikely event. But what if you buy 1,000 tickets? Then winning is not so unlikely. Here's how the look elsewhere effect is relevant to our situation. A 1,000-year flood is defined at a specific locale. So for example, a certain river could experience a 1,000-year flood. There are many different places in the US where a 1,000-year flood could occur. This is analogous to buying many lottery tickets instead of just one. So here's a question we need to ask. How many different, effectively independent possible places are there in the US where such a flood could occur? Without the answer to this question, we can't evaluate how strange the recent flooding is. To go back to the analogy of the lottery, we can't say how unusual it is that you won unless we know how many lottery tickets you bought. Now, answering this question would not be easy. To illustrate, for example, if your house is experiencing a 1,000-year flood, chances are your neighbor's house is too. So we shouldn't consider the flooding of your house and the flooding of your neighbor's house as separate events. They are not independent. At the other end of the spectrum, floods in areas separated by thousands of kilometers or months in time can probably be taken as reasonably independent. So how far apart do two places have to be reasonably approximated as independent? 100 kilometers? 10 kilometers? Okay, so as we stated earlier, the question is, how many different effectively independent possible places can a 1,000-year flood occur? How many flooding lottery tickets are being played? I have no idea what the answer to this question is. And I'm not going to attempt to answer this question. Instead, I'm going to try to illustrate how important the answer to this question is. We'll look into how the number of independent possible flooding locations affects the probability of having 5 1,000-year floods in 5 weeks. We will do this by taking 2 guesses at the number of independent flooding locations, and seeing how the probability changes. We will see that the probability of 5 1,000-year floods in 5 weeks depends critically on this input. And we should note these are going to be very rough calculations. Okay, here's wild guess 1. Take 2 locations in the United States. Let's take as our guess that flooding in 2 locations are effectively independent if those 2 locations are more than 100 kilometers apart. So under wild guess 1, what is the probability of 5 1,000-year floods in the US in a given 5-week period? Okay, the area of the United States is about 10 million, or 10 to the 7 square kilometers. If we divide the US into 100 kilometer by 100 kilometer regions, the area of a single region is 10 to the 4 square kilometers. So there are 10 to the 7 divided by 10 to the 4, which equals 1,000 such regions. The probability of a 1,000-year flood in a single given region in a given 5-week period, which we called a tenth of a year, we said is 1 in 10,000. As there are 1,000 regions, we would expect on average 1,000 divided by 10,000, or 0.1 thousand-year floods in a given 5-week period. So, on average, we would expect 0.1 thousand-year storms nationwide in a given 5-week interval. But we want the probability of actually seeing 5 such floods. We use a Poisson distribution where lambda is set to the average expected number, 0.1, and n, the observed number, is 5. So we substitute those values in, and we get a probability of about 7.5 times 10 to the minus 8. Okay, so under wild guess 1, we see that the probability of 5 thousand-year floods nationwide in a given 5-week period is about 7.5 times 10 to the minus 8. This probability is much larger than the incorrect calculations we saw before, but it is still quite small. Using wild guess 1, we would probably conclude that something seriously weird was going on. Okay, now let's look at wild guess 2. Here we're going to guess that occurrences of flooding in 2 locations are independent if the locations are greater than 25 kilometers apart. This is a factor of 4 smaller than the distance in wild guess 1. Okay, so now under wild guess 2, what's the probability of 5 1,000-year floods in the US in a given 5-week period? Again, the area of the US is about 10 to the 7 square kilometers. We're going to divide the US into 25 kilometer by 25 kilometer regions. The area of a single region is 625 square kilometers. This means that there are 10 to the 7 divided by 625, which equals 16,000, such regions in the US. Like before, the probability of a 1,000-year flood in a given single region in a given 5-week period is 1 in 10,000. There are 16,000 regions, so we expect on average 1.6 thousand-year floods nationwide in a given 5-week period. Again, we use a Poisson distribution. Like before, the observed number, n, is 5, but this time the expected number of thousand-year floods, lambda, is 1.6. When we plug these numbers in, we get about 1.8%. Under wild guess 2, getting 5,000-year floods somewhere in the US in a given 5-week period would be uncommon, but not rare. It is very reasonable that this would happen for some 5-week interval in a given year. Under wild guess 2, having 5,000-year floods in the US in a given 5-week interval is really not very weird at all. The answer is very sensitive to the number of independent flooding areas. Wild guess 1 and wild guess 2 gave very different conclusions. Without knowing how many roughly independent possible flooding areas there are in the U.S., we have no way of telling if having 5,000-year floods in the U.S. in a 5-week period is unusual. Again, the article implies that it is unusual, and it may very well be, but we cannot determine this solely from the information given. Okay, I want to briefly also mention a few other complications. There are 3 lesser points I'll touch on. First, we can ask if these floods really are independent. Second, we can ask what happens if they are not equally likely to happen at all times of year. And third, it's not ideal to choose the 5-week interval of interest already knowing what floods occurred. Okay, first point. We have assumed the 5 floods were independent. Were they? For example, were any of these floods from the same storm system? If the occurrence of a flood makes another flood that is not too far away in time and space more likely, then a cluster of 5 floods in 5 weeks may be more likely than the naive estimate implies. Okay, on to the second point. We assumed that 1,000-year floods in a given location are equally likely to occur at any time of year. What if they disproportionately occur during this time of year? This would also make a cluster of 5 more likely than naive estimates would imply. On the other hand, if they tend to not occur at this time of year, then the opposite conclusion applies. Note that both of these latter considerations imply that 1,000-year floods may not be sufficiently well described by the Poisson distribution. Okay, and lastly, point 3. It is dangerous to retrospectively choose a 5-week interval already knowing when floods occurred. In principle, the 5-week interval should be chosen before the weather in question happens. Choosing an interval afterward can introduce bias. Okay, so with that, let's summarize. Here we looked at a recent headline about flooding. The headline and its accompanying article imply that the recent flooding is very unusual. And this may well be correct, but we need additional information to actually ascertain that. Without knowing how many approximately independent flooding regions there are in the U.S., we cannot determine how unusual this set of events actually was. It's important to ask the right questions.